Okay, let's start. So today, we have a relatively tight schedule. We're gonna finish random forest, um, and also how to apply random forest to big data. Okay, so that's it's pretty um, aggressive schedule. So I'm sure. I mean, the people in this class you probably have heard of random forest before, and they probably have know some of it. Okay, so what I'm going to do today is more like try to fill in some details. Okay, so for those of you have know a little bit about random forest, um, there are some details. Okay, you probably I'm going to more like introduce like a why you need you can why random forest works. Okay, so some of this is a there's some like a I think it's you probably most of them have some like a superficial understanding about random forest, but exactly why it works and how it works, you may not be that clear. Okay, so this class is gonna fill in that. For those of you who haven't, who do not really know the random forest, okay, so this is a there are a lot of details into this as well. Now, before we talk about the around the forest, of course, you want to talk before you talk about forest, you need to talk about trees. Um, so we're going to start with the decision trees. So decision trees are one of the most popular learning methods, like commonly used for data exploration. One type of decision tree is called CARD. And CARD stands for classification and regression tree. This is the main tree we're gonna introduce for today. So CARD is a greedy top-down binary recursive partition that divides your feature space into sets of disjoint rectangular regions. And we're gonna see what exactly this means. And these regions should be pure with respect to the response variables. And also the simple model is fitted each model, right? So for example, like if you already partition your feature space into these rectangular regions, and then for each region, for each rectangular region, then the fitting the model into that region should be simple. You can either use the majority vote for the classification, or you can use this so-called constant value just for the regression, right? You just this is the once you have determined how do you partition your feature space, then the fitting is very simple. Let's see an example. So in this example, you have a simple data set. Okay, this data set only have two predictors. One is called TI, another one is called PE. So it doesn't really matter what this is mean, but just you have two features. And then the response variable, okay, response variable are just binary, okay, good or bad, right? So you is in the blue stand for the is a good response, the green stand for the bad response, right? So this is just like a two binary. There are some circles, okay? Circles, that means this will be your like for your task data set, where do you want to put it in, right? So this is our like prediction. The model training is involving this is you have this good bad, but for the last row is response is unknown. This is we want to predict, right? We want to know for this is having TI is 4.5, PE is M5, which class, which classification we should place this is red dots. So so-called greedy recursive partition along the TI and the PE. This is what we can do is at each node, right? So when we partition it, we will choose a variable and then partition. This is your group or the observations along this variable by determining the two halves. So then each partition we call it a node. So at each node we perform a split. Okay, the split is done this way. We choose a variable x and the value t, such that we have in this we minimize some kind of criteria. Okay, so the split will be in the left. On the left is all the value with x is less than t. They all going to the you're going to go to the left side, and all the value is bigger or equal to t. You're going to go to the right side. So like for in this case is we have two values, right? TI, two variables, TI and PE. So the first split is saying we want to choosing the variable will be ti. The value t is going to be 5. So therefore, we say if ti is bigger than 5, we're going to split them into one node. Ti is less than 5, we're going to go to the another node. If you graphically, this is a two-dimensional graphic. So the first line right here, this is going to be your first split. Okay, this is going to be your first split. All right, this is going to first split. So your first split is going to split your space, the feature space, into two regions, one to the right and one to the left. And then if you look at to the left or to the right side, the right side you can see majority dots are blue dots, right? So it's a good response. So therefore we can say all the regions, then we can classify this region to the right is going to be blue. Okay, so that means if anything, if it was ti is bigger or equal to 5, we say it's going to be produce a good response. So then after that, then the next split we can do it on the PE. Okay, so PE is saying if PE is not in the M1, M2, M3, then we're gonna be in the so this is a yes goes to the right. So is no is go to the left. So that means if PE is not in the M1, M2, M3, you're gonna go to the right node. So therefore, this is a M1, M2, M3. This is if they are in if they are in M1, M2, M3. So this is going to be in this region. So this region, this is going to be 1.1. Okay, so because this is after the first split, we're going to do the next split is according to this line. Then the last split will be because then once you go into there, you can see in the upper corner, the left corner, majority of them is going to be in the blue dots. So therefore, its classification is going to be the blue. Then you're going to go down to the bottom left. You can see in there you can choose another split, which is the ti is bigger than or equal to 2 or not. So if it's bigger than or equal to 2, of course you already have the split is the ti is bigger than or equal to 5 or not, right? So you know this guy is already so this is pi is bigger than or equal to 5. Okay, I guess I got it wrong. So this side is yes. Okay, this side is no. So therefore is not in this is a pi, in this is this will be yes. All right. So this side is no. Okay, so I split it. So therefore in the right, so it's not in here. Is not in here. That means it's in the M4 to M9, right? So it means upper corner. Then if pi is it does not belong to in this thing. So this is negative. That's actually within there, right? So it's in there. So it's going to bottom. Then is dependent on is bigger than or equal to 4 or not. If it's yes, then it's going to be green. This one be a green. So then the rest is going to be blue. Now back to the ones. This is the white dots. So it's ti is 4.5, and then the PE is M5. So if you want to do a prediction, you just go down the tree, right? Does it bigger than or equal to 5? It's no. So therefore we go to this node. So does it is not in the M1, M2, M3? So you can say it's not, right? So it's going to the node here. Then therefore the classification for the test side is going to be the blue point. Okay, so this is how the tree works. Now you can see each region. You can see here each region is a rectangular region, right? It's a rectangular region. So you can see partition them each. That's why it's called in the previous slides is called the partition is going to be rectangular. Now, I mean, if you do this, right, you can see there are actually many different ways you can do the partition, right? For example, if you look at this is unpartitioned region. Now, why the first split has to be in along the ti equal to 5? Why the first split? Why I cannot just do it here? Why I cannot do the first split is I can do this split. split it into like a up and bottom based on PE, and then I can do this split, right? Then after I do this split, I can do this card or do this card. Eventually, this is gonna be end up with essentially the same. You can see the almost the same classification, right? The only thing you can see here is instead of doing this split, I change to here. So if you do the prediction for the white dots, it's gonna give you the same classification, but it's just with different rules, because then the tree in the above I draw in here and tree down below, these are two different trees, right? Because they represent two different trees. Now, then the question is, how do we decide it? Because as you see it by eyes, there are multiple ways you can divide this your feature space, right? It does not seem to be unique. Even like the one I proposed above, you can give almost the same prediction. It almost is the same because if you really look at this, okay, the ultimate classification essentially is this. This is the ultimate classification, because the only thing is anything within this rectangle is green, anything outside is blue, right? Even down here you can see we can basically remove this line and remove this line. These are the ways to the sort of like the basically is classification, right? First of all, there are multiple ways we can do that. Okay. Second of all is when we do that, is this optimal or not, right? Or if it's optimal, what is criteria to determine it's optimal? This is actually the sort of like the hard part for the tree. So the tree method is okay. So this is so-called let's talk about binary partition for the card first. So the binary partition is at each node. Okay, at each node we try to partition your feature space into two components, two parts, right? Based on the one variable is less equal to some value. Then according to the rule, like in the rule to the left side, you're going to end up within if you partition feature space, end up to the right side. So this is as you can see, everyone is rectangle. Now, if we do it somewhere along to another way. So on the right side, okay, if I say if there are some rules which you can partition your feature space into a shape like what I show in the graph, like a bottom right. Can this be achieved by the so-called binary partition? Right, so then the answer is no, right? Because you can see in the region, they are so if you look at this region right here, this is not a rectangle region, right? Although you can say you can if you really want to, you can make this as you can do this to be making this as a two rectangle. But then if that's the case, if you look at this outer space, okay, this part is also not rectangular, right? So if it's not rectangular, then your partition, okay, it will not be, this kind of partition will not be achieved by so-called card algorithm. Then the other tree method may be able to give you this is kind of the shape, but not by card. Okay, if the card algorithm, if you're doing the binary partition, then your feature space has to be, if you can draw it out, it has to be rectangular. So therefore, this is one of the features for the card. For the tree, they are depending on the response variable. Okay, if the response variable is categorical, like we said before, is a yes or no, or you have multi-level, then we call this classification trees. Correspondingly, if your response variable is numeric, then your response is going to be, then in this case, we particularly call the regression trees. Okay, so regression trees and classification trees, they represent just like the logistic regression and the linear regression, right? So one is for the categorical response variable, one is for the numerical response variable. But then the underlying the partition almost the same, but the only thing that differ in their loss function, right? Is the criteria. What do we try to minimize? So the classification trees, including things like card, C5, firm tree, there are different kind of the classification trees. They have different features. The one we're going to talk in this class is card. Okay, card is referring to classification and the regression tree, right? So one of the features binary partition. It's one of the simplest trees we can do. So therefore, we're gonna work with this. The decision rules we can say is it's gonna walk through is based on this sort of tree. At each node, it basically is have a binary. You need to make a binary decision, right? You see, if you have a credit card or not, yes or no, you're gonna depend on that. You can go to your down partition your group like into two different components. Then if you have credit card, you have yes or no. Then if you have credit card and have a car, you're going to approve your credit card application. Otherwise, you're going to reject it. If you don't have a credit card, then depending on your age, is yes or no. If age is less than 30, approve. If age is more than 30, you can reject. So that's the this is kind of binary decision rule matches like a human thinking very well. Is intuitively, because when we try to making decisions, is more like we try to is kind of like I wouldn't say most cases, but if you have this kind of binary decision rule, it's easy for people to follow and also easy for people to understand, right? There's no ambiguity. Just ask at each time, ask question, yes or no, and then at the end you reach to a decision. So this is one of the advantages of the tree. The tree is the rules are simple and also it's intuitive and easy to follow. The only thing about the tree, this is what we're gonna say later on. I'm gonna introduce more details about trees, but this is also one of the maybe this seems to be very, this is an advantage, right? But also the disadvantage of the trees is the tree could be very unstable. Okay, so in other words is if you change your data point a little bit, okay, you may end up with a very different tree. Like just I drew it in here for this variable. If your data maybe change a little bit, then you may have a different tree. Although at the end it may reach to the same conclusion, but the tree itself, the decision process will be different. So this is kind of creating this so-called sometimes creating this is a instability to the tree. That's why later on we're going to introduce the random forest. It's kind of average out. We're going to build many different trees and average them out. That itself is it can be more stable, but it also lose the interpretability of the tree, because the tree, follow the tree, we know exactly at each step what we're doing, right, and how we get to this to our decision. But if you introduce like a forest, the concept forest, then how do you get into this decision would be that is like more like a black box. Okay, let's talk a little bit more about the trees. So the regression trees. Regression trees is let's use the regression trees as example to demonstrate how the card works. For the categorical response is similar. Okay, so will be the process similar. So suppose we have n observations, right, or 1 up to n. So we have in this xi will be represent our feature the vectors. Yi is our response. All right, so xi you can see this is a feature vector because it's having like a p variables. Now consider a partition. Okay, consider a partition of these n samples. Like see we based on some rules. Okay, we already did it. We already did this partition. We have partition the features space into M regions. Okay, so this is how do you do that? We're gonna come up to in a second. Let's suppose we already made the partition. Okay, we have M regions, R1 up to Rm, like we did here, right? So I have R1, R2, R3, R4, R5. So we already did this partition. Okay, you have these M regions. Then for each region M. Okay, so for each region, the best estimate for this region will just simply be the mean of the yi for those i's within this region, right? Because this is very simple. You partition your samples into like a capital M, this many groups. Then you say I want to estimate. Okay, I want to estimate the number for that group. You want to find one group to represent the region. So what number that number should be? The number should be simply be the mean of this sample, right? Because if you don't have any other information, you want to give an estimate to that group, that simply is the mean. So this is the mean would be for those for those objects that is belong to RM, because this is RM is again divided by the features, right? So if for those subject I belong to this region, then we just average, take the mean of their response variable. So that's the value you're going to give to that region. So finding the best binary partition in terms of the minimum sum of square is generally computationally infeasible, right? So hence we produce with a greedy algorithm. So if you end up with this if you have this M region, since it's easy, right? You want to give an estimation, just take the mean. However, to get into this M region, that is difficult, because how you can do that? So therefore, then this is the so-called the CARP is a greedy algorithm. So what we can do is we start with all of the data, consider a splitting variable J and a split point S. Then we can define the pairs of this so-called half plane. Is defined as R1. So the first the split is based on the J and S. So the R1 is going to be the Xj is less than or equal to S. R2 will be Xj is bigger than S, right? So if you can do that, then you can determine the first split. Then we can once you determine the first split, then we can go down use the same criteria to do the second split. So what does this mean? This means this basically so this is what it means is you have variable x1 up to xp, right? You have your variable y. So you have y1, y2 up to like yn. Okay, you have n variables. Then you have x11 up to x1p, x21 up to x2p, xn1 up to xnp, right? So this is your data. So what this is a proposed basically saying, you're gonna scan through all the variables, okay? So say you're choosing the variable xj, okay? You're gonna scan through like x1, x2, xj. You scan for each one xj. And then you're gonna consider all the possible partition you can making this is your data into two halves, right? Now notice here, say if you choose x1, that's starting from x1. So you're saying my splitting variable should be x1. Then when you split variables of x1, how many possible binary partitions you can have in terms of data? Anybody can guess the how many possible binary partition you can make in terms of data? Huh? n-1, right? Why is n-1? Because when you're having this, say you order your x1 in like from the highest to lowest, then those points are discrete. In theory, if you want to make a binary partition for the x1, you can have infinite cutoff, right? Because x1 is defined, say it's continuous, it's defined a real line. So any one of this value, it will make a binary partition. However, in terms of the data, right? Because the x1's value are given. So therefore, see this is your x11, this x12. So no matter you're cutting here or cutting here, it doesn't make much difference in terms of your final output, right? In terms of your data set. So therefore, when you scan through it, you only need to consider the values already in the data set, right? So therefore, when you do the x1, you basically just say x1 is less than, you're going to do x1 is less than or equal to x11, x1 is less than or equal to x1 or x21, and so on. So you just need to consider each you're going to consider each value in the data for the x1. Then you can determine all the possible partition for the x1. So therefore, the first partition, right? In the first partition, in your in here, what you're gonna do? We're gonna scan through all the splitting variable. J is all the possible value, and then you have in the splitting point S. You're gonna through all of them. So therefore, this scanning is gonna be n by p, right? It's gonna be n by p scanning because you're gonna scan through all the possible value. All the possible variable, and for each variable, you're going to scan all the possible values. So therefore, you're going to do this is you're going to have in a n by p possible partitions, right? So among these n by p possible partitions, then you choose the one which is giving you the smallest the errors. Okay, by say your cutting is right here. Okay, this is cutting right here. So therefore, you partition your data into like two halves, right? Into two halves. Then for the first group, you're going to take in the mean of y1 bar. This is a y2 bar. Then you can calculate mean square error for each or the SSE for the region 1 and region 2, and add them up to the which split going to give you the smallest one. That splitting point will be a first split, right? That's going to be a first split. And then you can do this recursively, okay? You can do this recursively. Say, for example, you already, this is your first split, okay? So this is the first split, x1 is less than or equal to some value t, right? Then you partition your region into two halves. Then the next split you're gonna say is for the things on the right, okay? So basically what you have now, when you go down to the x1 is less than or equal to t for this part of data, you don't need to consider the other half, right? Because these are becoming independent. So when then next time we split, you're going to scan through all the p variables and scan for all the values within this region. Then you determine next splitting point. Okay. Right. So the similar you can do it for the bottom is for this one would be x1 is bigger than t. Then you have sort of half of the data. So you're gonna scan through all the possible variables and all the possible values, and then you can do that recursively until you cannot find any improvement, right? Any improvement to your data, then that you stop over there. So when you can stop, when like in this case is like an obvious condition is when you think you're gonna stop the splitting. Like when under what condition you're gonna see you cannot improve the splitting anymore. Say it again. Into one, yeah. Well, you can actually stop early, right? So one of the condition you're gonna stop. You're right for the regression trees. Typically, if you're using this criteria, eventually you're gonna end up with each so-called terminal node, right? Is the end node. It only contains one sample, right? But however, then the condition would be if your node, if you like after you make the partition, if all the value in that region they are the same, you will not be able to partition anymore, right? Because say if you partition here, if you have this y1 up to like y5, their value are the same, okay? Then it's SSE or the arrow, sum of square arrow is just be 0, because if the value are the same, their mean is gonna be the same. It's gonna be the same, right? So therefore, no matter then, if that's the case, you will not be able to like further improve your errors, right? This is called a pure node, right? When node is pure, you will not be improving. The same thing for for regression tree is less. The equal value is less common, but if you are doing classification, yes or no, right? Binary, then that's going to be more common because many node or region could probably going to be pure if before you go down to like each node contains one variable. Okay, so this is how building the tree. This is the tree is if you continue through that, that's then you can build a tree. That's how you grow a tree. If you grow a tree like that, typically it's gonna be over if you grow the tree like that, then the tree usually is gonna be overfitting, okay? Because like I said, eventually if you grow the tree, this is the node right here, okay? It's called the terminal node. And then for the regression tree, the best thing would be one terminal node, it only contains one variable. In that case, your error term is just be 0, right? Because then for each node, if you only have one observation, then it means just itself, the error is 0. But then if you're having that, then for sure you're gonna overfit it. So therefore, if you grow a tree like that, that tree is probably too big, right? It's too big. So then people develop a concept called prune a tree. So the tree pruning is like this. Suppose you already grown a tree up to so-called T0. That's like the biggest tree you can grow based on the criteria like I just mentioned, right? So you grow a tree, it's called T0. You want to collapse, okay? You want to collapse some of this its internal node. So you have a tree. Now you have a tree like this. Okay. So the tree, then the tree, if you have a tree given like this, the pruning just basically say you want to collapse some of the node into one node, right? So collapsing, like say you can collapse this is the two node, collapse this internal node, this is gonna then this is gonna be this is gonna be a T0. Then once you collapse this two into one internal node, then you're gonna become a so-called shallow tree, right? So it's having so this is so-called pruning. You can do it like recursively to prune your tree by cutting off the branches. Eventually you're gonna go back to the node, to the origin node. Some concept is here. So suppose you have a tree called T. Then we say this is a number. So NM is going to denote is how many the terminal node we have. Okay, so this is for you have a tree, you can count this terminal node. This is and you can denote by NM. Oh no, NM is number of the observations belong to the region M. So sorry, this is the absolute value of the T. Okay, this is called cardinal. Cardinal T denote the number of the terminal nodes in T. So this terminal is by the so-called, this is like more like absolute value of T, right? Is how many terminals you have. Capital NM, this is defined as number of the observations in the region M. CM hat, this is defined as the average value for the region M. And this is QMT, this is the MSE, the mean square error for each region, right? For each region M. So we can define this is a complexity, cost complexity criteria is defined like this: is a summation M from summation over all the terminals, and for each terminal we use NM times the QMT. You can see this will be just basically the sum of errors, sum of square errors for each region, right? Plus alpha times this is the size of the tree, the tree size. So the idea is we're going to find for each alpha, we can find a subtree. The T alpha is belong to this is T0 is kind of like T alpha is so-called any tree that can be obtaining by pruning T0, right? So to minimize this is a criteria. Now notice, if you notice that this is a complexity criteria, there are two components, okay? One is this is the first component. You can see this essentially is the SSE, sum of square errors, right? This is SSE. This is representing like all the errors, right? The second term, this is representing the complexity of the tree. Because the more terminal node you have, the larger the absolute value of T, right? The cardinal of the T. So the C over T, just like any model selection criteria, it has two components. One is model accuracy. That is characterized by the mean square error, by the smallest error. One is another term is going to be model complexity, because the more terminal they have, the more complex the model is. So this is basically trying to find try to find a balance between your model accuracy and the model complexity. Okay, just like if you are familiar like the criteria like AIC, BIC, they all use the same idea. They have one term is model accuracy, another is model complexity. So this is using so like similar idea. They are ways. Okay, there are ways to call the weakest link pruning. This is the procedure. You can prune the tree. Now this is more like has been this procedure is building like an average tree process. So you can just call the function tree. They can beautiful. Essentially, what it does is you try to collapse the internal node. Okay, you have to collapse this internal node to find the collapsing which can give you the smallest improvement on your sum of errors, and that improvement, this is going to be your first pruning. Okay, you're going to be any pruning give you the smallest. Any pruning give you the largest the improvement on the sum of square errors. Then that's what we first pruning, and then once you do the first pruning, for example, if I do this if our pruning tree is become this, then this is a new tree, right? Then you can do based on this new tree, you can do the same thing. You collapse any internal the node give you the largest improvement. Then you can sort of like iteratively you can find a process. Eventually, you can prune everything and go back to your root node, right? The root node it will be contain everything. Now along the way, you will have a sequence of trees. That sequence of trees is guaranteed. Okay, it's guaranteed that your T alpha it will be included in that sequence of trees. So therefore, you can basically for that sequence of tree, which is when you use the weakest link pruning, then you can plug it, because remember when you're generating the sequence of this the weakest link tree, you don't need the complexity. You just based on the sum error squares, right? So therefore, then you can plug in this is a C alpha T for each one of them, and you just find out which one give you the smallest. This is so like penalize the loss is then that tree will be your T alpha is your final tree. So I mean this process is mostly very automatic. So you just know this is the criteria and there's a way we can achieve that. Okay, so that's this is how you prune a tree. Typically, if you have a tree, if you just grow a tree according to the criteria we had it before, without pruning it, it's almost guaranteed you're going to overfit your data. Okay, so prune a tree if you're just using a tree model. Tree pruning is very important. Now, in terms of the classification tree, then the classification tree is almost the same, similar to the regression tree. The only thing is different is when you try to estimate, you see you classify into each regions. Then in a node or the region M, we're going to represent the region M with so you have NM observation there. So then the proportion of the class K observation in the node M, so you have M, you have K levels, right? You have K levels. So then the case category, okay, in the node M we define as PMK hat. This essentially is we count for the region M, we count how many observations are in the case category. So we sum them out, we count how many of them divided by the total observation in the region M. So that's is proportion, right? So then, because why we calculate? Because for each region M, we need to have a label, right? We need to have a label. So to determine which category this region is going to belong to. So essentially, what we can do is like the maximum of this is whichever the most category this region M contains, it will be its label. Okay, it will be its label. So this is a classification tree. The criteria for the classification tree, like when you try to grow the tree, right, or the prune tree, the classification we use, there are three classifications. One is called the misclassification error, the Gini index, and another one is called cross entropy or the deviance. Now, misclassification error is pretty simple to estimate, right? So Km, this is representing for the region M, we label it as a classification K as a category K, right? Because if the Km will be the Km, which is basically argmax of P hat mk, okay, with respect to k, right? Because for each region M, so we see how many we have. We have k categories, and then the category within the most observations, it wins the vote, right? It wins the vote. It will be labeled as it will be the label for the region M. So therefore, for the region M, you can see here, for you're going to sum up over all the regions. In each regions, you're going to say for each regions, you're going to say for you are not, okay, you are not in the arrows basically is for those ones is not the correct or the label, right? Is not a category K, then we count, basically count those observations which are not the category K, you sum them up, you divide by the total number of NM. So then we classify this. So this is our classifying arrows. Then at the end, we sum up over all the regions. You will have so-called misclassifying arrows. So this classifying arrows is pretty intuitive. We want to minimize the error, right? We don't want this error to be too big. The second one is called the Gini index. Gini index, this is basically for each region. We calculating the product, okay? The PMK hat and the PMK prime hat. That's when the K is not equal to K prime. So eventually, then what it has is P hat times 1 minus P hat MK. So this is Gini index. If you look at it, this is essentially is look at the variance of the P hat, right? This is look like a variance of term. If you look at this is the graph, okay. So if you only have two categories, then the misclassification error. This is basically saying how did it looks like. This is Gini index is the blue line, and the last one is entropy. Misclassification error and the Gini index. These two are, I think, to me is pretty easy to understand because a misclassification error, that's just counting how many errors for the classification, right? It's intuitive. We should know how many what's the error. Gini index is somewhat also pretty is also easy to understand because let's see when the k is equal to 2, okay? Gini index, if I say big equal to 2, you're gonna see what it means. So if it big, if you only have two categories in each node, right? So Gini index is basically saying when this is a so you only have two categories. So you're gonna have in summation. So then this is gonna be P1 times 1 minus P1 plus P2 times 1 minus P2, right? P2 hat. And since you only have in two categories, P1 hat plus P2 has to be equal to 1 because for this is because since you only have two categories, so therefore this is essentially the Gini index will be going to be 2 times P1 hat times 1 minus P1 hat. Okay, it will be equal to this. This guy maximize at P1 equal to 0.5. Okay, and when it's going to be 0, reach the minimum when P1 hat is equal to 0 or 1. What does this mean? It means if the P1 hat is P1 hat is equal to 1, what does it mean? That means for that node, every single observation is going to be the category 1, right? It's going to be a pure node. So which means we think that's a good node. That's a good partition. Because when we partition, we want each node contains, it won't be a pure node, right? Contain the same group, then that's a good partition. So therefore, P1, when P1 equal to 1, then your error basically is 0, which is good. So we want that. When P1 is equal to 0.5, what does this mean? That means your category 1 and category 2, each of them have half-half. Right? So if each of them have half-half, that means this node, you have 50% is category 1 and 50% is category 2. So then that node is not a pure node. That node basically is indecisive, right? It's indecisive. So therefore, it's not a good partition. So we don't want that. So in that case, we want to minimize this criteria. Basically, is we try to making our node as pure as possible, right? By if it's not pure, then we're gonna split again, right? So that's basically what it does. The ones is less intuitive, okay? This is called cross entropy or the deviance. The cross entropy is saying you want to sum up over all the categories using the p hat mk times log p hat mk. For those of you who are like, if you are not familiar with the concept of entropy, okay, this is kind of very, very difficult for you to understand. I have this entropy. The concept is actually can be borrowed from information theory. So I can give you guys an example. Okay, to demonstrate this is to basically to introduce this what is the concept of entropy. Right? So then you can have a direct view for all the entropy. Otherwise, if you look at entropy, it's just a formula. Okay, there's no intuition behind it. Let's see if you have in 4 letters A, B, C, D. Okay, you know you only your space the letter space is only this 4 letters A, B, C, D. Now, if I don't give you any information, now I hide it. Okay, I have a number in my mind. Okay, now I ask you guys to guess what the letter is. How many guesses you think you need? Like I have one letter, is one of these 4, okay? I have in mind. So if you want to guess, you can only ask yes or no questions. So if you want to take a guess, how many guesses you think you need to guess my letter in my mind right now? That should be easy. How many guesses would you need? 2, right? So you can basically do is basically you can partition them. Is it in A or B? Right? If yes, then you that's one guess. Then you narrow down to the half. If not, you narrow down to the other half, right? So then I can tell it's yes. Then you can say is A or B. Then is it A? Then you can, if it's yes, then you carry it, right? If it's no, then you can it's B. So it's 2 guesses. Now let me give you another piece of information. Here will be, I'll pick these numbers, okay, based on some, not random, but based on some probability. So I'm going to have 50% is going to be A, 25% is going to be B, okay? 12.5% is going to be C, and the same 12.5% is going to be C and D. Now, how many guesses? You can think like what's the minimum guesses you think on average, what's the minimum number of guesses you need to guess my letter? Do you think you can beat 2? The answer is actually yes, okay, because I don't have time today you really need to think about this. The way to do that is you can ask the question whether it's A, then if it's yes, then you guess it. If it's no, you can ask it is B, then you can guess to the B, then you can ask is the C. You can guess then it's going to be C or T, right? So this is yes or no, yes or no. You basically, if you have this information, okay, then you're asking the question. The order should not be just binary because you have this you have additional information. So what you need to do is basically you should guess based on their probabilities. Since you have 50% is A, then your first probability should be based on probability. Okay, so your first question asking is it A? Because you're going to have 50% chance. You only need 1 guess because now you guess the number of guesses to be A is just you have 50% chance. You only need 1 step, right? Now, if it's B, you will need 2 guesses. Then the next question, if it's not A, then you subsequently then this the probability space you can also, because B has a higher probability. So the question you cut off, you should ask is B or not. Okay. So therefore, if it's number B, it's going to be 2 guesses. Then For the C and D, each one of them, you want the 3 gases, right? So therefore, the expectation, okay, the number expectation of the gases should be 1 times 50% plus 2 times 25% plus like 3 times another 25%, because then 3 gases you have 2, 1 to a power 5, right? So therefore, then this number is 1.75. So on average, you will need less gases to gas in the letters. Now, how does this related to the classification tree? Because this is criteria, okay? This is number of gases. You can also write it as basically the summation I from 1 to n of probability, okay? So you're going to have in the probability for each gases. You expect a number of gases is expecting a number of probability times log of 1 over pi. This log of 1 over pi, this is basically this will be a number how many gases you will need for this to have the number. Say if it's half, then this is log 2, okay? So this is the half, this will be log 2 of half, right? So this is basically 1 over half is 2. So this is you will need 1 gases. If it's B 25, then log 2 of 4, you will need 2 gases, okay? So then this essentially is negative summation of pi log of pi. Okay, this is sort of like the entropy concept is coming play. Entropy basically means when you having this pi is more close to random, okay, then that means this entropy has more. It can contain more information. It can contain more information. That means there may be a lot of noise in there. Now, if your entropy is low, when that means when this is pi is equal to like when the pi is equal to 1, when the pi is equal to 1, this is summation pi. So if pi is equal to 1, log of pi is going to be 0, right? So this term is going to be 0. Other terms is all going to be 0 because other pi is going to be 0. So this is 0 times 0. So then it's also 0. So if sum of the pi is equal to 1, that means then this essentially your entropy is 0. That means your information is fixed. Okay, then there's no ambiguity about the sequence. So when there's no ambiguity, say for example, this is 100%. You know this is 100% 0. Okay, 100% A, 0% for the A, B, C, D. Then you don't have any ambiguity. When you have no ambiguity, that means what? That means knowledge. Okay, so that means knowledge. So when you summarize this information, for example, knowledge means if you have 3 letters E, M, C, if you have these 3 letters, then you can, if you can randomly shuffle them, there's no meaning, right? But if I write E equal to MC squared, all of a sudden it has meaning. That represents knowledge. So the entropy, less entropy, basically means knowledge. That is we try to do is try. That's why we want to minimize the entropy is basically in the classification. That means we want to making that group, okay, for each node want to be pure. So therefore we want to having the equivalency, we want some knowledge about that node, okay, because we can see something about that node. Okay, so this is a cross entropy, or the deviance is come into play. Let's move on, because this is typically when you grow a tree and prune a tree, you want to choose in different criteria. Okay, so you see if you grow the tree based on gene index, then when you prune the tree, you probably it's better off you choosing the cross entropy, because if you use the same criteria, that's basically how you come down, how you go back up, right? So there's no then this is create less variation. So these are the tree. As I mentioned before, the tree, the real the problem tree is not very stable. So then the people define based on this is so-called random forest. Random forest basically what it does is we try to, instead of rely on our decision based on one tree, we try to build up many different trees. Okay, So there's many different trees. Then we can, after building many different trees, what you're going to do is we can average the trees, right? Average the decision from the tree. So this method is belong to a group method called bagging. This is called the bootstrapping aggregation. So how are we going to build the random forest trees? Okay, let me go through the algorithm first. Then I'm going to talk a little bit intuition about the random forest. So what it does is you're going to grow. You're going to choose and say I want to build up like a capital B trees. Okay, so this is capital B is the total number of trees you want to build, and then for B, small b, from 1 to B. So small b is a tree index. So for when you try to build a tree, so first step is you want to draw a bootstrap sample Z star from your origin training data. Everybody knows what is bootstrap sample. Bootstrap sample essentially is sampling with replacement, right? So you just draw the sample like one by one, but with replacement from there. So therefore, when you draw the bootstrap sample, your sample could be like the same. Okay, you like one sample maybe draw twice or even 3 times or more, multiple times. So that's a bootstrap sample. Then the total size is the same. Okay, the N is the same as the origin training data. So you draw a bootstrap sample of same size as the origin training data, and then you're going to grow a tree. Okay, the random forest tree, so-called TB, to the bootstrap data by recursively repeating the following step and on each step based on the following value. So for each node, when you grow the tree, you're going to choose M variables at random from your total P variables. So your total, you have P features, you have P variables in there, but for each splitting, okay, you don't use in every single variable. Like when you find out the splitting variables, you don't use in all the P of them. You're only choosing a small set of M, okay? And then you pick the best variable splitting point among this M variable being chosen. Then next time you split the node into two daughter node, okay? So when you go, then you can go back to for the B, you're going to go back. Once you split them, you go to the next node, you pick another M, and then you do the splitting. Here is a weird thing, okay? Here seems pretty weird. When you grow the random forest tree, okay? So for the first node, you choose M variables. Okay, you grow. This is different, okay? So you have this is a root node, okay? This is a root node. You choose M variable, you grow it into two subnode, child node, right? Now, when you try to grow, this is the left child node, okay? Shall we use the same M variables being picked at the very beginning, or shall we use a different M variables? Say your P, say you have in total P is 100 variable, right? M equal to 10, okay? So you total you have 100 the features. In the first split, you only use 10 of them, okay? You use 10 of determine the split. Now, this turn of say is x1 up to x10. You choose in first step. When you try to split in the child node, shall we use the same 10 variable? You split in the root node, or shall we choose a different 10 variables? The different ones. So the algorithm says different, right? So then remember this variable down here. What you can choose? You can choose like 11 up to x20. It could be, although it's the same tree, it's different. When you're building the card tree, you have in the set of variable. Then when you grow the tree, you scan the same variables, right, along the way. But when you grow in the random forest tree, then the variable growing in this root node and its child node may be different. So every single node, when it tries to grow a node, this could be x21 to x30. Okay, they are choosing different sub variables to grow the tree. Now the question is why? Why do they? Does it sound weird? Right? This is a when you to grow a tree like this is a very strange way to grow the tree. Well, we'll come back to this point, right? So then once you have in this, basically you for each random forest tree, you're going to grow in this fashion, and you grow to B of them. this capital B could be, say, 1,000, okay? This capital B could be 1,000. You grow like 1,000 random forest trees. So then when you try to do the prediction, then you plug in your new variable, yeah, new sets into there. So you will have 1,000 or the capital B predictions. All right, so you see B is equal to 1,000. You will have 1,000 the random forest trees. You grow them. Then when you do the prediction, you basically just each tree is going to make its independent prediction, and you average out to there. If it's regression, you just average out their tree value, regression value. If it's classification, you just average out the category, right? So you find the most the category is then that of the tree. So this is an algorithm for the random forest. This is a graphic. This is the graphic the showing. That's essentially is just basically go through what I described. Now, my question now is, why do they when they grow the tree, they choosing different variables M for each node? Is it intuitive or is kind of strange? Does it feel intuitive to you guys? Well, first, there are actually quite a few different questions, right? Firstly, why do you have to draw the bootstrap sample? Now, algorithm is easy to understand, okay? But then what I'm trying to discuss with you guys is why, okay? Why do they do that? The understanding is one thing. Understand the algorithm is one thing. Understand the motivation is another thing. Now, why do they have to draw the bootstrap sample? Why do they have to just grow the tree? Why do they have to using only a subset of the variables M instead of like a whole, every single or the whole feature space? Why do they, when they split in the node, the different node, they're going to using different subset of variable to grow the tree? So these are the details. So why do they do that? What's the reason behind it? Now the reason is actually is pretty simple, because when they try to making this is the final decision, what do? They're using some like a democratic so-called ensemble method, right? Some democratic vote to do that, right? So it's regression taking average. If it's classification, you find the majority votes, right? So in order for this to work, there are assumptions behind. Okay, the assumption is the tree itself, it has to be independent from each other. If the trees are not independent of each other, in the more extreme case, if the trees are all the same, then by doing the example does not have any benefit. You build a 1,000 tree. If the 1,000 trees they are identical, when you take an average of majority vote, doesn't improve anything, right? So the reason they do this is trying to making each tree as independent as possible. Okay, try to make the trees independent as possible. Now, this is belong to like for the average. When they try to do the ensemble, the data points, right? So this is trying to just make sure when each time when you try to have in the what kind of data, the sample or the training data, each time they will be different. Of course, there are some overlap, but at least they will have some difference. Then when you try to build and grow up the tree, each tree want to rely on different subset, right? So and also building the node differently, it also can. These are all the things which can kind of like making the tree be less independent. So why do you want to do that? The reason is we can see from a simple calculation. Okay, suppose you have n decision makers. Okay, your decision makers, and then so for each decision maker, okay, let's say for each one of them, okay, let's see the probability, okay, they're gonna making the right decision, okay, they're making the right decision is equal to pi. Right, so you have n decision maker. Each one of them can make the right decision is pi. This pi is some probability, okay? This pi could be very small, like 0.55. That means each one of them, if one making decision independently, only 55% chance they will be making the right decision, right? Now, that be Y will be the number of people, okay, number of people making right decision. Okay. So then based on the with majority vote, okay, with majority vote. Okay, so with majority vote, then the probability, okay, probability of making the right decision as a group, okay, is going to be probability of Y is bigger than n over 2, right? So first of all, the Y, like why do the people making the right decision? So this Y is actually follow a binomial distribution, right? The binomial n half. Right? Why is that? Because each one of them is basically the Bernoulli, right? You have n of them, and then Y is basically is Y equal to 1. Then each person making right decision is going to be 1, making wrong decision 0, right? So then their Y is basically binomial NP. So we know that. So the probability within majority vote, the probability of making right decision as a group using majority vote. Majority vote basically saying that Y is bigger than half of the total, right? Y is bigger than n equal to q. This is the probability. So this probability is depending on part, is depending on n, right? So then if you calculate the probability, this is a Bernoulli, this is a binomial, this is the n. Now within that, you can actually you can calculate it by the probability. I'll just give a few examples. Okay, if n is 30, okay, if n is 30, pi is equal to 0.55. This basically means each one of them is not a good decision maker because they only make a right decision like a 55% chance, right? It's only barely higher than like guessing. You guess, you can making like if you finally decision, right? Guessing is like 50% chance, right? So each one of them is like 55% of chance. Now, suppose you have 30 of them, you have like a 30 lousy decision maker, and you put them into a committee using majority vote. What do you think this probably going to be? Okay, if you give a guess. Anybody take a guess? Is like you think it's gonna be higher than 55 or is lower than 55? Come on, should be higher, right? So otherwise, why bother doing the whole process, right? So the probability is gonna be 0.645. Okay. Now, if you increase this is the number, okay, to 100. Okay. This probability gonna increase into 0.17817. Okay. If you increase into 200, it's gonna be 0.97. So what does this mean? This is basic thing. If you can have, you form a committee. Each one of them, you don't have to be right at every single time. Okay, you just be a little bit better than random guess. Okay, random guess. Then if you form a committee of 20 using majority vote, you can basically improve your probability making the right decision from like 0.55 to 97%. This is a very good decision maker, right? This is a very good decision maker. Now, this whole thing, this committee is called ensemble. This is the basis for like a decision tree, right? Decision tree basically form, you have building a bootstrap trees, you have form a committee, and then you do the votes. This is the whole thing behind it. But this has a very important assumption behind it. That assumption is you have to be independent. Okay, there are two assumptions. One is that every decision maker, they have to be independent from each other. Second, they have to be slightly better than noise. Okay, you cannot say I'm making the pi is equal to 0.4. I'm just like even I'm very bad at even worse than the random guess. If you're making the wrong decision every single time, formal committee is not gonna make you better. Okay, it's gonna actually make it worse. So you have to be one, you have to be slightly better than the average, the noise. Two, you have to be independent. So this same thing is like for the Democratic, like when we do the voting in this country, like we do the voting, the same thing applies. Is if you can maintain your independent thinking, okay, when you go voting, you don't have to be a great the decision maker, okay? You just me. I'm just do a most of the time. I mean, but I still can be wrong like 45% time, like 49% time. As long as I can slightly better than the noise and I'm making my own independent decision, then you can contribute to the process. The worst thing would be everybody think the same. Okay, so if you're thinking the same, then the whole thing is going to lose its value. So that's why it's very important in the future when you go out to the work. That's why the independent thinking is so important. Okay, because you got your mind or your decision going to be influenced by other people. People can talk about this information, other information. You're going to say, "Oh, I agree with you." Then as soon as you say, "I agree with you," your mind influenced by other people. Then you lose the independence. You lose this is a power for you aggregating your contribution to this process. Okay. I mean, this is a separate topic, but back to this random forest. So this is the core idea for this is why we do this kind of weird thing. Is try to making your tree as independent as possible. Okay. Now, of course, when you try to grow, you're still coming from the tree, still coming from the same process. So therefore, you cannot grow your tree the bee as you see in the control. The more commit number the members commit member is, the better decision you can make, right? But in the random forest, you cannot grow this bee to a lot because the more random forest trees you have, then the more dependent you're gonna be within the previous trees. Because you only have the limited sample, right? You only have limited variables. So therefore, B cannot be too big. Okay, B typically is like a 500, 1,000. That's probably depending on how many sample you have. That's like a B also has a limit. Okay, is this clear? Is this a hopefully now you can have some instead of like understanding the what I'm trying to see here is instead of just follow the algorithm. Okay, I'll try to give you guys some intuition behind why it works. Okay, why the random forest works, and then based on those principles in the future, you can design your own like the algorithm. So the other consideration like how to choose B, how to choose M, and the split, how to split. These are the things you guys can you can read it because I don't have like 10 more minutes, so I need to move on. So you can check this by yourself. There are features and advantage for the random forest. There are another concept. Okay, another concept for the random forest is the so-called OOB arrows. OOB arrows, I'll say very briefly. You can fill in the blanks. This is for every bootstrap tree, for every random forest tree you're making, right? Then this tree, since you're taking bootstrap sample, roughly, you're only taking like 2/3 of the sample to build up the random forest tree. Therefore, basically, since it's a bootstrap sample, therefore you have about 1/3 of the sample which is not using to build a particular tree. Okay, so this is the sample left for each tree. What's left is naturally can serve as a sort of test sample for that tree being built. Okay, so you only build, say, the tree number one. You're only using the bootstrap, only taking like a 67% of the or 2/3 of the data points to build a tree, and another 1/3 naturally is a test sample for the other tree. So therefore, you can so-called, this is called OOB arrow. This is outer back arrow. That's basically you can basically measure like for each tree what is a prediction on the outer sample. What's the arrow, and then you having say 1,000 of them, right? You have 1,000 test sample. You average out, you get an OOB arrow. So that OOB arrow is the arrow when you having all the data. Okay, so this is OOB arrow. It can also be a very good measurement for the random forest if you want to project to the for the test data set, what's error be. This OOB is typically is a very good measurement. Now using this OOB we can also to measure so-called feature importance. Feature importance basic thing is when you're having all the variables included, you have an OOB called E hat. Okay. Now for each predictor XP, what we can do, we can permute this predictor. Permute basically means we scramble, okay, by making this P. Once you scramble it, then basically you're making that variable to be noise, right? So then based on that, you can compute using you can compute the OOB based on this is a scrambled or permuted XP. Okay. Now notice you only permuted one variable. Okay, you're keeping all the other things the same. The idea is if this variable is very important, if you permute it, make it into a noise, then your prediction error should go up. Right? So if it's an important variable, if you permute it, make it into a noise, then your prediction error should go up. If it's a noise to start with, you permute it, still noise, shouldn't impact your error, OOB error too much. So therefore, the importance measurement basically using the arrows when you after permuting this is a k, the xk, and the minus the original error. This will be the larger this difference is, that means the more important this xk is, right? Like I said, if your xk is very important, if you permute it, make it a noise, your ek should increase a lot, right? Because then you lose a very important, basically lose a very important predictor. So therefore, based on the difference ek minus e hat, ek hat minus e hat, you can rank your features one by one, and that rank is your feature importance. Right? That's why when you see the random forest give you feature importance, this is how they do it. Okay. Lastly, how do we apply the random forest to the big data? To apply the random forest to big data idea is very simple. Is using the same principle, right? We try to building many small trees, and then for each tree we try to make them as independent as possible. Okay. So therefore, when we try to, then the idea for this is that we try to build the trees. The tree, each sample, for each tree, we instead of taking a bootstrap sample, which is taking, say your n is say n is like equal to 1 billion, right? This is going to be a huge tree. You cannot fit it. Instead of building a huge tree, when we do the sample, we only sample a small portion, like say 10 to the 6. We only sample like 1 million of it. So the sample size for each tree is going to be a small, based on small samples. Okay, so that's how we do it. This is based on observation is feeding a single tree with a large data point, like say 100 million data points, can perform worse than feeding just a few models with 10 million data points each. So so the way for the random forest trees is, so the point is still maintained, right? So we try to building some independent trees, but now instead of using like all the data points, we just pick a small sample, small subset, fraction of them to building the tree. So then by doing that, you're gonna still building a lot of small trees and then aggregate them out. Then the whole thing still works. The only thing we left is the only question left: how many trees we should build? Okay. Suppose you have n data points, then this data point could be very, very large, right? Like in billions level, and distributing to the distribution file system. So if you want to train m different models, so this is the m different trees we want to build. Then for each model, it contains like k data points, and this k typically much less than n, right? Like I say, that this n is 1 billion. This k could be like 1 million. It's much less. Now, what we want to do is we want to make sure when we're building these m models, this m model should have enough coverage to our data points. Okay, that means you make usable data. Then if km, m is total number of models, k is number of data points used by each model. So k times m, this will be the total observations you feeding for the whole training, right? For the large data. Let's say this is km equal to t times n. So then the percentage of initial data points is not going to be including in any of the training models, right? It's going to be this. So for any data points, it's gonna be missed. Okay, it's gonna be 1 minus 1 over n. That means the data points to be chosen is 1 over n. 1 minus 1 over n. This will be the data points will be missed from one peak, right? So if you pick in the data points, total is k times m this many times, and then for this many peaks, you miss all of them. Then this probably just be this is just 1 minus 1 over n times k times m, right? Now k times m, like I said, is t times n. So therefore, this will be 1 minus 1 over n times t. And this probability will be e to the minus t, okay? And when the t is equal to 5, that means t equal to 5, what does it mean? It means your coverage is like 5 times the original data points, right? So when t is equal to 5, then roughly, then this probability is 0.0067. In other words, if you're making your coverage to your own data is like 5 times, then you're missing any one of the data points. You didn't including any, because the more data points you include in your training, then the more information you gain, right? So then the probably going to miss any one of them is going to be 0.0067. Right? It's very small. So therefore, you should looking for at least, say if you for when you're training data sample is k, then you should making this number m should be roughly, okay? Roughly is m will be t times n divided by k. So that's how many models you need to train, okay? So that's so this is the last piece for the random forest. Okay, so that's I mean it's a little bit rushed, but I finally we got through to the big data. And I mean, if you have questions, let me know. Okay, so yeah, I know it's kind of rushed, but a lot of details I could spend like another class to do that. Now, Wednesday is Thanksgiving. We have no class. Okay, hope everybody have a good break. However, don't forget your final project is going to be due on the weekend. Okay, on the next Sunday, 5 p.m. So don't enjoy your holiday break, but don't forget you have a project due up there. So then in December 30th, which is Sunday 5 p.m., you're going to do on the December 1st and December 3rd. We're going to do the we're gonna making this is your group project. Okay. So on the Monday class, make sure you come early. Okay, because then I need to a little bit of time to set up. So I want to start the class right on because we're gonna have 5 presentations each. Then basically we cannot lose like a lot. So we're gonna start the first group. We're gonna start at like a 9:30 sharp. Okay, we're not gonna wait for anybody. Okay, that's all. I'll see you guys on Monday.